This video is going to take a look at applications of logarithms and exponents. And the main application we're going to look at is going to center around the basic exponential equation. And that is going to be the function f of t is equal to p e to the kt. Now each one of these variables is going to mean something to us. The p is what we call the present value. Another way of thinking about it is where you start. The e, we've already seen that as Euler's constant, is approximately equal to 2.718, and that's that e natural base for our natural log that we've talked about before. K is the growth or decay constant. And finally, t, the variable we're usually most interested in working with, is the amount of time that's going by. So, for example, I might be asked to find out how long will it take an investment to quadruple. At 8%, compounded continuously. Well, we've got some type of starting amount that's going to need to quadruple. So we're going to go from some principal amount, and we want it to quadruple to 4 times that principal amount. So 4 times the principal amount is how much we have at the end. The principal is what we start with. E to the k, the constant of growth, it's 8% growth continuously. So 8% is 0.08. And t, we're solving for the time. Well, before we can change anything to a log, we need to get the exponent part alone and by itself. So we'll divide both sides by p. And in fact, those p's all divide out, and we just get 4 equals e to the 0.08t. And what's nice here then is we can convert this to a log problem. We know it's a natural log with a base e of the 4 would equal the exponent of 0.08t. All we have to do to solve for t to get the time alone is divide by 0.08. And now we'll know how long it's going to take by simply doing the natural log of 4, closing the parentheses, divided by 0.08, we get 17.34. 17.34 years. Any investment at 8% will quadruple every 17 years. Let's take a look at another application. The Moses Lake population has grown 1.8% per year. To 20,305 in the year 2014. What was the population in 2000? Well, we know f of t is equal to pe to the kt. Looking at what we have, the 1.8%, that's going to be our k as a decimal point 018. 20,000, that's the starting value that we're given, our p, in the year 2014. Now we could make the time 2014, but that usually makes it a bit more difficult. So let's call that our 0. Year 0 is when the population was 20,305, and then we'll use our time to say how far away from 2014 we are. So the question's asking about the year 2000. So for our time, that's 14 years ago. We're going to use negative 14 to represent that 14 years ago. And so now we have f of negative 14 is equal to the principal value, the present value, which we know, of 20,305, times e to the k, which is 0.018, times t, which is negative 14. Our calculator now can do the work from here. 20,305 times e, which is second ln, raised to the 0.018 times negative 14, and we get 15,782, let's round it, 15,782. Was the population in the year 2000. Let's look at another application, one that gets used a lot for this exponential equation PE to the KT. And that is this concept of half-life. The half-life of titanium 44 is 63 years. How much of a 52-gram sample is left after 46 years? So for those of you that haven't taken a science class with half-life in it, a little description of what half-life is. Half-life basically says if I've got this block of titanium 44 made up of all of these atoms that are just in here in a grid, all these atoms are locked together, and what happens is the electrons and the protons and the neutrons in there are all moving around. And sometimes what happens is a beta decay where it loses either protons or electrons or neutrons, and when it does that, it changes the type of element it is. It's a different element because it's got a different number of protons. It's called beta decay. What happens is there's a probability that any one of these will suddenly decay away at any given moment in time. So what happens is there's less and less titanium actually available. And the way the probabilities work out is it takes about 63 years and half of them are gone. Then it will continue to decay, and in 63 years another half of them will be gone. And then it continues to decay another 63 years, and another half of them will be gone. And then 63 years later, half of them will be gone. The idea is every 63 years, half of the elements, or half of the atoms, are gone. Essentially, after 63 years, there's a 50% probability the element has decayed away. That's half-life, when there's a 50% probability that the elements have decayed away. So what we need to know is what is the decay constant that corresponds with a 63-year half-life. If we start with P, at the end of a half-life, there is 0.5 P remaining. Half of P. And our formula says we take the principal starting amount times e to the k t, and we know the amount of time it takes to get a half-life here, in this case, is 63 years. So again, we divide both sides by p to get rid of that p on both sides, and we have 0.5 equals e to the 63k. Change this to a natural log problem. Base e of 0.5 equals 63k. And we finally get the k alone by dividing both sides by 63. Our calculator then can tell us what the natural log of 0.5, close the parentheses, divided by 63, hit enter, negative 0.11. Constant is negative 0.011, sorry. This is the decay constant that corresponds with a 63-year half-life. Now that we know that 63-year half-life, we're ready to answer the question that's actually asked of us. How much of a 52-gram sample is left after 46 years? 52 is the principal that we start with. E to the k, which is negative 0.011, times t, which is 46 years. Put the calculator out of the way. Now what I'm going to show you is going to be a nice trick to use when the line above it has the k in it. You see the 0.011 right above where my cursor is. That's going to be important here as I type in 52 second e, and then I really want to put the k here. To grab that previous answer, I'm going to hit second and then the negative sign, which takes the previous answer. That way I don't get a round-off error, times 46. And when we hit enter, there's 31.35 grams of titanium 44 remaining of my sample. So I have 52 grams. 46 years later, it's probably going to be 31.35 grams. It decays away. This particular application is going to be important enough to us that we're going to do another example like it. How about this one? The half-life of the element fermium 253 is 3 days. How much of a 12-gram sample is left after 1 week? The first question we're going to have to attempt to solve is, what is the decay constant that's going to correspond with a 3-day half-life? So if we start with P, it's going to decay away to half of P, or 0.5 P, when multiplied by e to the k t. The amount of time it takes to go from P to half of P is 3 days. Divide both sides by P to get 0.5 equals e to the 3k. Convert this to a natural log of 0.5. That's going to equal the exponent of 3k. And then get the k alone by dividing both sides by 3 on our calculator. So we have the natural log of 0.5, close the parentheses, divided by 3 is negative 0.231. Negative 0.231. Decreasing 23% per day, really. Now we're ready to actually answer the question. How much of a 12-gram sample, that's the principal I'm starting with, the present value, is left after 1 week? That's our time, but be careful not to put 1 in there. Notice the units on our half-life were in days. So t also needs to be in days. So we've got 12 e to the k, which is negative 0.231, or we're going to use the previous answer, times the amount of time, which is 7. So 12 e to the, notice that previous answer again, second negative sign gives me the previous answer, times 7. Enter. My 12-gram sample is down to 2.38 grams. 2.38 grams. After 1 week. This stuff is very unstable. It doesn't stick around very long. It decays away pretty darn quickly. So all these examples we've seen, population, continuous interest, half-life, doubling time, same idea, all use the same basic equation, Pe to the kt, Pe to the kt. There are equations, though, and problems, application problems, that are slightly more involved. More involved equations. And these equations I wouldn't expect you to memorize. Instead, I would give you these equations. And they just require us to know where to plug what and how to solve for what. One example of this is what is called the logistic equation. The idea behind the logistic equation is, let's say there's some population of animals that's growing in an environment. They can't grow indefinitely at the same pace. Eventually they'll run out of food, or they'll run out of water, or a predator will move in and take advantage of them. Basically, there's a maximum sustainable population in an environment for some organism. The further away they are from that maximum, the quicker they can grow, because there's lots of resources available. But when they start to get close to that maximum sustainable population, the population is going to start to level out and stop growing. There's an equation that models this. If you start with the population, call the starting population B for beginning population, with a growth rate of K and a maximum sustainable population of M for maximum, it grows over time. We'll use T for time, using this function. Q of T is equal to M over 1 plus B e to the negative K T. So if a population of sparrows grows at a rate k equal to 1.31, and we're going to say the population is currently 1,200, but the system can support 2,400, twice that. How many sparrows will there be in 7 years? So here we're given the constant for these sparrows and how they grow. We know the population is currently 1,200. That's the beginning population. And that the system can support 2,400. That's the maximum that it's going to be able to sustain. We're interested in when time climbs up to 7 years. So Q of t, Q of 7 is going to equal the maximum, 2,400, divided by 1 plus the beginning, 1,200, e to the negative k, 1.31, times t, which is 7. So plugging that in our calculator, 2,400 divided by parentheses 1 plus 1,200 e, which is second ln, to the negative 1.31 times 7, close the parentheses. Whoops. Make sure at this point you get out of the exponent. You might have to, depend on your calculator, close the parentheses on the exponent or scroll out of the exponent. Then close the parentheses on the denominator. Which is an interesting point that I didn't stress as I typed this in, is I need to make sure that denominator is in parentheses, so the calculator knows that entire thing is in the denominator. And what we find is there's about 2,133. 2,133 sparrows. So it's grown from 1,200 to 2,100. Maximum it's going to sustain is 2,400 over time. So that's one way I might be able to give you an equation that involves exponents or logs, and you should be able to figure out how to solve and answer the question. Let's look at one last problem before we wrap up our very last video for pre-calculus. Newton's law of cooling. The idea is how fast something cools down is actually an exponential problem. Newton found out that an object at temperature T sub 0, starting temperature, initial temperature T0, surrounded by air temp of T sub A, let's do capital T, air temperature T sub A, will gradually cool to a temperature T over time, lowercase t. We're just going to try and confuse you with all these t's. Capital T sub 0 is your starting temperature. T sub A, that's the air temperature. Regular T, that's the temperature it ends up at. Lowercase t, that's the time. The formula is the final temperature is equal to the temperature of the air plus the temperature starting minus the temperature of the air times e to the k T. So if you leave a hot pizza at 350 degrees on the counter, where air temp is room temperature of 72 degrees, and the constant for this pizza is equal to negative 0.08. How long until the pizza cools to 100 degrees? Well, 350, that's the initial starting temperature of the pizza, so that's going to be our T sub 0. The air temperature is 72, that's our T sub A. We're told our K is negative 0.08, and we want the pizza to cool to a final temp, or T, of 100 degrees. So when we plug this into our formula, we get 100 equals the air temperature of 72 plus parentheses the starting temp of 350 minus the air temp of 72 times e to the k, which is negative 0.08, times T. Simplifying what's in the parentheses, 100 equals 72 plus 350 minus 72 is 278. E to the negative 0.08 T. What we're solving for again is in the exponent. And so to get it out of the exponent, we're going to need to write it as a natural log. However, we can't do that until that part is alone. We're trying to isolate the part with the exponent. So first we'll subtract the 72 from both sides to get 28 equals 278 e to the negative 0.08 T. Divide both sides by that 278, and e to the negative 0.08 T is equal to, let's just keep this as the fraction because the calculator is going to do the dirty work for us, 28 over 278. Converting this to a natural log, because we already have the base e of 28 over 278 is equal to negative 0.08 T. So to get T alone, we just have to divide by negative 0.08 on both sides. And now we will know our time when we type this into our calculator. Natural log automatically opens a parentheses, 28 divided by 278, close the parentheses, and then divide by negative 0.08, hit enter, and we get 28.7 minutes. So this pizza at 350 degrees in 28 minutes will cool down to a mere 100 degrees. Again, these more involved equations I don't expect you to memorize, but you should know how to use them. In addition, you should also know the basic exponential equation. You should be able to use it for interest. You should be able to use it to double or triple or quadruple your money. You should be able to use it for half-life. And you also should be able to use the equations I give you. So take a look at the homework assignment. It's our last one for Pre-Calc 1. We will see you in class tomorrow.